recording now. You should have received your midterm marks back, those of you who wrote the midterm, if you haven't written it yet. And those of you who wrote it at a different location will receive it soon. So everyone did well. No one did extraordinarily bad. The average was pretty high. I think it was 79 or something. The final is significantly harder, just so you know. So I keep saying that, and maybe I'm lying, maybe I'm not, you don't know. It's kind of fun, isn't it? So I know in a couple of days, a bunch of people will be asking me to meet and talk about their questions. I do not negotiate marks, especially multiple choice questions. If you want to see your exam, what I will do is, and please don't all email me asking for this, just if you really need to, email me. I will send you the numbers of the questions you got wrong, and during the lab session, the TA will have a copy of the exam, and you can go up there and check with him to see which questions are the ones you screwed up on. Okay, mind you, if you remember the bonus question, that was a fun one, right? Who knows the right answer to the bonus question and wants to talk me through it? Son was traumatized, yes, madam? You think it's B? Why is it B? Right. Now, how many of these have 50%? Just one. So it's 1 out of 4 again, which is 25%. But if it's 25%, there are 2 of them with 25%. Which one do you choose? But they're both right, so it's 50%. But there's one 50%, so it's 25%. It's a paradox. There's no right answer. Know what I mean? Which is why everyone gets the point. If you wrote down anything for it, you get the point for it. Right? So that's why I encourage you, I hope you wrote something down for it, because if you didn't, you don't get the point. All right. Isn't stats fun? Paradoxes. Isn't that great? Okay, so moving on. Now, those of you who didn't write something down for 70, you're really mad at yourselves, aren't you? All right. So, we last time before the exam, we talked briefly about the ANOVA, or ANOVA, which stands for Analysis of Variance. That wasn't on the midterm, but it will be on final, obviously. And we talked about there are 3 types of ANOVAs, the one-way, the two-way, and the n-way. Who remembers the differences between the one-way, the two-way, and the n-way? Nobody remembers, because it wasn't on the midterm, so nobody got to pay attention to it. It comes down to the number of, I always confuse independent and dependent variables, the number of dependent variables. That's right, right? So if you're looking at, are the mean ages between 3 classes the same or different? So you've got one dependent variable, that's the number of classes, so it's a one-way. If you're looking at the number of ages, or the average age of between the 3 classes and 2 genders different, then we have 2 categorical variables, so it's a two-way. And if you're looking at the average age between 3 classes, 2 genders, and 4 nationalities, that's 3-way or n-way. So it comes down to the number of categorical variables. Guaranteed this will screw somebody up. So remember that, it's the number of categorical variables, not the number of levels or groups in those categorical variables, but the number of variables. Okay? Now in this class, mathematically, we're only doing the one way, computationally. But I want you to know how to identify a two-way and an n-way. And it comes down to, again, the number of categorical variables. Simple as that. So how do you do a one-way ANOVA? We did an example last time. We won't do another example because it's really straightforward. It's just plugging in the numbers and figuring it out. So first thing you have to figure out is the number of groups or levels in your categorical variable. So if I'm saying 3 different classes I'm comparing mean ages to, then k is 3 different classes in that one variable. And n is a total number of people. So I've got 30 people in this class, 80 people in the other class, and 70 people in the third class, and my total n is 180, right? So once you've got k and n, we compute the degrees of freedom between groups and the degrees of freedom within groups using these formulae, k minus 1 and n minus k. Straightforward stuff. It gets tricky when we have to compute F, which is our test statistic. And that is given by that formula there, the mean squares between groups divided by the mean squares within groups. And last class, we went through line by line how to do that in a spreadsheet format. So you're going to have lots of practice doing this on your second data analysis assignment, which I will upload this week. If you don't see it by tomorrow, somebody email me, remind me. Again, my brain's a sieve, I forget everything. And it's my weakness, so I don't mind you emailing me, reminding me stuff, because I will forget otherwise. Right? And remember, as always, if the thing in the table is less than the thing that you compute, then it is statistically significant, and we reject the null. Right? We won't go more into that because it's straightforward. It's just like t-test, except one level more. So, we talked briefly about the difference between parametric and non-parametric tests. And the difference is defined this way. A parametric test relies upon a parameter. So a parameter, again, is a characteristic of the reference population. So I know we're repeating ourselves a lot here, but the mean age of this class is a statistic. The mean age of the university is a parameter. Right? So with parametric tests, we assume that a parameter exists, and we assume there's this superpopulation that we're trying to estimate. With non-parametric tests, none of the above apply. So we've already seen one non-parametric test that we've done in this class. Do you know which one it was? One that doesn't assume a particular distribution and doesn't measure a parameter. We've done one already. It's not the t-test. It's not the ANOVA. It's not the z-score. What does that leave us with? You've forgotten everything you've learned so far. Really? Really? It's the correlation. The correlation doesn't attempt to say that this particular sample comes from somewhere else. It doesn't attempt to say that if I'm correlating your height to your age, I'm not saying that everyone's height is correlated with everyone's age. I'm saying this sample's age is correlated with this height. So that particular non-parametric test just deals with the sample. It doesn't make allusions to anything else. So the parametric ones we've dealt with so far are these: the Z's, the T's, the ANOVA. And the non-parametrics are the correlations, particularly the rank correlations that we'll deal with later, and the chi-square, which is what we're going to talk about today. As you progress through your health sciences career, and if you don't go deep into statistics, probably the three most common tests you're going to do in your life are correlations, chi-squares, and t-tests. Probably more of these two than anything else. And the reason for that is everybody kind of understands correlations. Correlations are fun because you can, even though we know that correlation is not causation, it's fun to pretend that it is. So it's a fun, lunchtime conversation. This is correlated with that. Well, that's not fun. And chi-square, because, as we'll see in a second, chi-square allows us to associate categorical variables with each other. Is there a relationship between nominal variables? And even though we already talked about how continuous variables give us more wisdom and more nuance, like age and weight and height, in the real world, people tend to code things as nominal variables. Yes, no, male, female, Canadian, non-Canadian. Did you pass, did you fail? So for some reason, the real world tends to like categories like that. And so the chi-square takes on great prominence. So non-parametric tests are used commonly when the outcomes are not measured as continuous variables, as we mentioned, and when the assumptions for the parametric tests are violated. So what does that mean? It means if they're not, normally distributed, things like that. But in general, it's mostly this. It's mostly when we have categorical variables. It's funny, I can't read when I'm standing here. I think it's a left brain, right brain thing. It looks gibberish to me. I gotta, over here. Oh, it's all clear now. That should be somebody's thesis. Okay. I had a stroke last night. I don't know. All right. So the kinds of non-parametric tests you need are depends on the number of groups you're being compared. So you can correlate two things. You can't correlate three things. You can, however, correlate two categorical variables with multiple levels inside. What province you were born in? You have 10 options there, correlated against, the gender you are, so 2 and 10. So it depends on how many levels you have. And the type of comparison you're making. So are we doing between subjects, are we doing within subjects? And don't worry about that too much about that. The more you do ANOVA stuff, the more clear that distinction will become to you. So I want to introduce 3 tests today, but only one are you required to know how to do. The one you're required to know how to do is the chi-square test, and the 2 you're not required to do are the Mann-Whitney U test and the Kruskal-Wallis test. In fact, all I need you to know about these 2 is how to spell them and the fact that you apply them to ordinal measures. That's it. Okay. And the reason I want you to know about them is that people like to put the chi-square on places where it doesn't really apply. And I want you to be aware that very often it doesn't apply. And most commonly where it doesn't apply is with ordinal measures. So if you're comparing 2 groups that are nominal, like, is there an association between taking health sciences and being female, right? Because most health science students these days are in fact female. We can probably do that analysis quite quickly. So we have 2 variables there, health science versus not health science, and female versus male. That's 2 groups and nominal measures. We do a chi-square for that. This may sound familiar. It may sound like a relative risk or an odds ratio, right? There is a distinct difference there. With a relative risk and an odds ratio, one is a risk of the other. Yeah? The math is substantially different and the application is substantially different. So keep those things separate in your mind. Right? Put the relative risk and the odds ratio aside right now. Now we're talking about our 2 variables that may not be risk and outcome. Are they associated with each other? In other words, are the proportions in one different from the proportions in the other? Now, if we're comparing two ordinal measures, let's say your rank in this class, first rank student versus second rank students, and whether or not one is female and one is male. It's a rank, so it's ordinal. We'd use the Mann-Whitney U test. For 3 more groups, let's say it's whether or not you're a health sciences student, a biomed student, or a non-science student. There are 3 levels there. And you've got, again, gender. We can still use the chi-square, but if it's ordinal, if it's your rank in this class, first, second, or third, versus gender, then we do the Kruskal-Wallis test. So again, just put those away, memorize the names, and when you apply them, but that's all we're going to do. Just recognize that they're there. We will only do chi-square in this class, but I want you to know what those other tests are and when you'd use them. So far, we've looked at what to do if you're comparing the means of 2 samples. What test is that? Shout it out. T-test, thank you. Yay. Okay, what do you do if you're comparing the means of 3 or more samples? Thank you, ANOVA. And now, what do you do if you're comparing 2 continuous variables that are related? That's a correlation. So we've done all that already. What we haven't done yet is 2 categorical variables that are related. Not risk and outcome, which is relative risk, but relationship, and that's the chi-square. It's not an x square, it's a chi-square, it's a Greek letter chi. So here's the example we're going to work through. The example is this, it's from the textbook. We have 100 patients, and they're receiving this thing called a heparin lock. Heparin is anticoagulant. The lock, I don't know, something biochemically, right? And they're looking at whether or not complications arise depending upon if you apply the lock for 72 hours versus 96 hours. And we want to know whether the duration, 72 versus 69 hours, is in some way related to whether or not complications arise. So we have 2 nominal categories there. Can you see the 2 nominal variables? What are they? The 2 categorical variables that we're associating. This is part of the challenge of doing this kind of work, is reading the question and figuring out what the categories are, what the variables are. So I told you there are 2 of them, and they're categorical, and they are? Right, so duration and whether or not there are complications. Okay. 2 nominal variables, obviously a chi-square. Had they been ordinal variables, it would be a Kruskal-Wallis test. Or Mann-Whitney U test, because there are 2 of them. Okay. In other words, we're looking to compare the proportions in each of these groups. So the proportion of complications in the 72-hour group and the proportion of complications in the 96-hour group to see if they are statistically different. That's what we're comparing. This is called a Pearson's chi-square, technically. There are different kinds of chi-square. There's a walled chi-square and things like that. Don't worry about that distinction. Be aware that various statisticians have added nuances to the basic chi-square estimation that are applied in different circumstances, but the core idea and really the core of the formula remains the same. So for your purposes, it's just a chi-square. But when we talk about Pearson's chi-square, we're talking about this very basic 2x2, or in many cases 3x3 association. Right. So again, is the proportion of patients getting complication the same in both groups, 72 versus 96-hour groups? That's what we're really testing. So what's the null hypothesis? The null is that the proportions are equal, or we say they're independent. That's another way of phrasing it. So the null, nothing's going on, they're independent, they're not associated. What's going on in 96-hour group has nothing to do with the complication rate versus what's going on in the 72-hour group. The alternative is going to be they're not independent. They are related. In other words, the proportions are not equal. Okay. I just said this, didn't I? All right. Okay, so what do we do? How do we do a chi-square? We create a contingency table again, that wonderful 2x2 table we were so fond of creating back in the relative risk days. We have our observed values, expected values, and degrees of freedom. This is what's going to screw you up, observed versus expected. We've already dealt with degrees of freedom with the t-test and the ANOVA. Now we computed a different way for the chi-square, and I'm going to define what these two things mean in a second. To set you up for it, observed is our data. That's what we have. But what did we expect to get? What did the mathematics convince us should be there? And if these two are the same, if the observed is the same as the expected, do you think the null is true or the alternative is true? Look on your face. Hey. If the observed is the same as the expected, is something going on or is nothing going on? In other words, is there a relationship or is there not a relationship? Is the null true or is the alternative true? Remember, science is conservative. We always expect nothing to go on, right? So if the observed is the same as the expected, that means nothing's going on. So we want the observed to be different from the expected for there to be statistical differences here. So keep that in the back of your mind, and they may help you parse through this process. So here's our data. Probably you can't see the headings here. So here we have the first group, which is the 72 hours of lock. Here we have the second group, 96 hours of lock. And here are the incidence rates of the complications. These had complications, these had no complications. Obviously, this looks a lot like the contingency tables we had for odds ratio, where that would be an exposure, that would be the outcome. You could think of it like that, but put that aside right now. It's chi-square from now on. Okay, so here our data is here. So this is what we observed. This is what the data came back, the experiment came back here. Over here we have our totals. We call these totals marginals because they're in the margins of the contingency table. And the way we're going to compute our expected numbers has to do with the marginals. We're going to do some math with the marginals and populate these places here that are red with numbers that mathematically should be there if in fact the distribution were random. That's really what we're testing, is we expect there to be a random distribution if there's no relationship. So if the random distribution is not observed, then there is a relationship. Okay. So assumptions of the chi-square test before we actually do it is that there's a rambling sampling of the observations. Yeah, that's more or less true. Right. We're not choosing these people for their responses to the heparin lock. Each observation is independent. That is, whether or not I choose this comes up has no bearing on whether or not the next one comes up. They're independent of each other. And each cell, these are the two biggest assumptions. So each cell must have an expected frequency greater than 0. And we're going to compute expected frequency in a second. And each cell must have an observed frequency greater than 5. This is the kicker, really, in real life stats. non-statisticians miss out on it. So the textbook says 10, but most agree to 5. So when you populate your table with your observed data, if one of these cells is less than 5, you can't do a chi-square. So when journals send me papers to review that have questionable statistics on them, one of the first things I look at are whether or not the assumptions of the tests that they've applied have been violated. This is one of the most common violations. In fact, I recently examined a PhD thesis which had a bunch of these being violated, and so the conclusions made in this thesis were all wrong, which is a very problematic thing to encounter in a PhD defense. Right, so it's an easy thing to look at quickly. And if, in fact, there are fewer than 5 items in one of these boxes, you can't do a chi-square, you must do something else. The thing that you can do that's most common is called a Fisher's exact test. Right? So a Fisher's exact test is a version of chi-square that accounts for situations where the cell sizes are less than 5. You can always do a Fisher's exact test. If you don't want to do a chi-square, it applies all the time. It's just harder, so people prefer to do a chi-square. SPSS will automatically do a Fisher's exact test for you if a cell size is less than 5. So when you try this out in the lab, try populating a cell size with a situation where it's less than 5 and see if the output says Fisher's test instead of chi-square, because it should, because SPS is clever that way. So what is this observed and expected nonsense? It's the formula. So the chi-square formula is this. We subtract the observed and the expected, we divide by the expected and we square them. Remember I said, if the observed is what you expect, nothing's going on, well, if they're the same, they become 0. All disappears, that's why. So we care about the differences between the observed and the expected. How we do it? So here are our observed numbers again. Here are the marginals. What we're going to do for each of these cells, we're going to multiply the marginals and divide by 100. So for this one, we multiply that marginal and divide by the total. In this case, it's 100. For this one, we're going to multiply that one by that marginal and divide by the total. For this one, we're going to multiply this marginal by that marginal and divide by the total, and so forth. So again, those are the marginals. And here are the formulas for the expected outcomes. So again, here, 50 times 20 divided by 100, and so forth. Elementary school stuff. And the reason is, if these are the sums of each case, then the random distribution will be defined by the degree to which these sums are offset by the total. That's the math explanation. Do the math, we get that. So here are expected values, here are observed values. They're pretty close, right? They're pretty close. So one might be tempted to say, well, they're close enough, so probably nothing's going on. Probably the observed are the same as the expected, and we're not going to reject our null. But let's do the math anyway and find out. So here is our spreadsheet with our observed values and our expected values. Cell 1, 2, 3, and 4. We subtract them, we square them, and we get that. So that's our chi-square number, 0.25. What do I do with that? Much like the t-test and the f-test, we look up in the back of the book. But first, we need our degrees of freedom. So for the chi-square, the formula for degrees of freedom depends on the number of rows and the number of columns. So here, how many rows are there? 1, 2. 2 rows. How many columns are there? 1, 2. Okay, we're not counting the marginals, just the main contingency table. 2 and 2. Therefore, our degrees of freedom is just 1. 1 degree of freedom. We look in the back of the book to page 416. For a chi-square 0.25 and 1 degree of freedom, we get 3.84. And the rule is always, if the book's number is bigger than your number, you cannot reject the null. So we failed to reject the null. And what do I conclude? What was the original question? The question is, why did I take this bloody class? The original question was, is there a relationship between incidence rate of complications and the duration of the heparin lock? What do I conclude? Is there isn't there one? There isn't, exactly, right? We failed to reject the null. So therefore, the null is in place. The two rates are the same. Complication rates are unrelated to duration of heparin lock. So here are the steps again. You state your null. You create a contingency table. You check your assumptions. The biggest ones being, are the cell sizes 5 or greater? Right? And now for the expected ones, are they 0 or greater? And compute the expected frequencies, compute chi-square, and look it up in the back of the book and answer the question. So chi-square is not limited to 2x2 tables. The example I gave was a 2x2. It could be 4x12, it can be 8x6, whatever it might be. If it is, more categories, it's people tend to interpret them incorrectly. The interpretation at the end of the day is, are these two variables associated with each other? That's all you can conclude from a chi-square. Not whether this one is greater than that, just are they associated? So in other words, is there a relationship between the make of car and whether or not they stop fully at a stop sign? So the make of car is Ford, Chevy, Toyota, so that's 3 levels for my one variable. Stop at stop sign. I can say yes or no, or fully, partly, not at all. So now I've got a 1, 2, 3 by 1, 2, 3, a 3 by 3 table. Okay. So the size C table here would be 3 by 3. It's critical that you get clear that this is just 2 variables, each one with 3 levels. It's not 3 variables, it's 2 variables. One is make of car, and the other is stoppage at sign. So, that's not useful. So, as I mentioned, if the observed is equal to the expected, then they cancel each other out. We subtract them. That means the chi-square distribution, because this is, after all, stats or everything distributed, is symmetrical around 0. 0 is where nothing happens at chi-square. In other words, the smaller the chi-square, the chances are the less likely it is there is significance. As I mentioned, if any cells have a value less than 5, you cannot do a chi-square. Instead, we do Fisher's exact test. We will not do Fisher's exact test manually in this class, so don't worry about that. But as always, I want you to know when to apply it. And when you apply it is when you have a chi-square situation where an observed cell count is less than 5. Right, so in SPSS, that's how it looks. You just click on descriptors and crosstags, go to tests, and so forth. Now that's your homework. Fast lecture today. Isn't that great? Out in 20 minutes. Any questions? Okay, I will post the audio for this on the website. Thank you.